There are a number of tricks that make use of the property of inertia. I have here a beaker containing water. You could use a glass as well, and sitting on a piece of paper. And when I pull the paper back and forth, the glass or the beaker moves along with it. Now, if I give it a really quick pull, I can slip the paper from underneath the beaker without the beaker itself moving. Let's repeat that again. Give it a quick pull, and the beaker stays in place. It doesn't tip over, and that's because the beaker has inertia. It resists moving. And when I pull the paper slowly, the gravitational force causes friction with the paper, and that frictional force is enough then to move the beaker as I move the paper. When I pull rapidly, the frictional force is not great enough to cause the beaker to move along with the paper, and so the paper slips from underneath the beaker, and we can then leave the beaker sitting on the desk top. You can use a juice bottle in the same way. Move it back and forth, give it a quick pull, and the juice bottle stays behind. So we're looking at the property of inertia, resistance to changes in motion. It's at rest, and so it wants to stay at rest unless there's an unbalanced force acting on it. I have a coin that fits just on top of a test tube, and then we'll put a piece of paper between that, hold it in place, and then I'll give it a sharp blow with my finger. I'll hold the paper at one end, give it a sharp blow with my finger, and you can notice that the coin stays in place. Let's do that again. So we've got the coin sitting directly above the test tube and the paper between the coin and the test tube. I give it a sharp blow with my finger, and the coin remains on the top of the test tube. Again, that has to do with the property of inertia. The coin will resist movement, and because I'm moving the paper very rapidly by hitting it with my finger, it causes the coin to stay in place. I've cut a plastic ring from a pop bottle. It needs to be about 1 centimeter wide, and I've set it on top of the juice bottle, and I've placed a penny on top of that. Now watch what happens when I hit it. The penny drops right into the bottle. Now it depends a lot on how you hit it, so let me do it again. So watch what happens when I hit it again. The penny goes way up in the air and doesn't go into the bottle. So it has to do with how you hit it, and you can really impress your students again with this little trick. The first time that I hit it, I made sure that my finger did not touch the far side, but hit only here. And so when I did that, it actually causes the ring to collapse, go away, and the penny drops straight down. The second time, I deliberately hit it on the outside here, which then forces the ring to go up, throws the penny up into the air, and it doesn't land in the bottle. So let me show you again. So just be careful how you do that. When I do it this way, it goes directly into the bottle, and if I do it the other way on the far side, then it goes up. Here I have a book suspended from a stand using some embroidery thread. If I give the bottom thread, which is tied around the book, a sharp pull, you can see that the string breaks and the book is still suspended. If I pull the bottom string slowly, the upper string breaks rather than the bottom string, because the upper string not only has to support the book, it also has to support the force that I'm pulling on it. So it has an additional force acting on the upper string than on the lower string. When I pull the bottom string quickly, it actually causes the bottom string to break because of the inertia of the book. So the book is actually resisting changes in motion, and therefore the bottom string breaks. Here we have a roller skate with a ball on it. If I push the roller skate and let it collide with the edge of the desk, you can see what happens. The ball keeps going because of its inertia. When I push it here, the ball and the roller skate are essentially one, and so the ball travels at the same speed as the roller skate. But when the roller skate suddenly stops, the ball, because of its inertia, keeps moving. There's no force holding it back, and so it keeps going. Now, if we tie the ball in with the strap like this, and then we collide it, the ball now becomes part of the roller skate, and the force is absorbed by the strap, and the ball then doesn't fly forward. And that's, of course, the principle of the seat belt. That the seat belt holds a person in place so that when a car is in a collision, you are now part of the automobile. The seat belt will constrain you and prevent you from flying forward because of your inertia. So if the car suddenly stops, the seat belt holds you in place. Without the seat belt, you keep going at the same speed that you were going at when the collision occurred.